Okay, everyone is probably familiar with a car odometer. This is a mechanical version. Yours is probably electronic in your car. But we use these to count, essentially count the number of miles your car has driven. So the number on the farthest left spins the quickest, and every time it gets to 10 or a 0, it flips the next number adjacent to the left over. And when that number gets to 0, it flips the next number over. And it continues like that, and essentially it counts. Here is oops, that's the same thing. So here is the guts of a typical mechanical odometer. What you have is a bunch of cylinders that can freely rotate, and each one has the numbers 1, 2, 3 through 0. Well, when you get to 9, you go 0 is the last number. So there's 10 numbers on each of these cylinders. And the cylinder on the right rotates, and every time it gets to the 0, it causes the cylinder to the very left of it to tick one extra mark. So here's how it would start out. So this first column is your ones column. Second column is your tens column, hundreds column, thousands column, and then 10,000s column. So here's how this. So the way this keeps track of counting is the count. So we start out with 0 things. So if we get to 1, then 1 would appear here. 0, 0. This still would stay 0, 0. And two, same deal. You could maybe think of this as objects. 2 objects, 3, so on and so forth. 4. So this thing would keep spinning. At some point, you're going to get to 9, 0, 0, 0, 0. And really, this is 9 objects that this thing has counted, or possibly miles. 9 miles. And then, when you go that next mile, it gets back around to the 0 again. And when this hits 0, it flips the next column to 1. And these, of course, stay 0. And so this represents 10 objects. And then this thing continues. So it goes back through this, and then there'll be a 2 here. And I think most of us are all familiar with this. Eventually, when this gets back around to a 0 again, this will flip to 2. And it'll just keep going like that. And it's accumulating counts. So this is 11, this is 12. So 12 is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So it's accumulated 12 counts of something. Well, counting like this, where we have wheels with 10 numbers on it, we call this a base 10 system. And that's the system that we all are very familiar with and that we universally use. But in a way, it is kind of arbitrary. It is kind of arbitrary that we use a base 10 system. And a lot of ancient societies also used a base 10 system. Like, for example, the Incas. And over on the right, this is what we call an Inca Quipu. And the Incas were a South American civilization at the close to the beginning of the last millennium. The system, they have a number of strings, and there's a system of knots that they have on here, and it's set up in a base 10 way, so that So the way you would use this is that you would count the knots, and the knots were spaced out in such a way that, like, the bottom knot was the ones, the second group of knots was the tens, and the third group of knots was the hundreds. And you could certainly go higher if you wanted to. So you could see this is 131 or 202 because they leave a space for zero, or a space for zero. 43 over here. So it was a system, and it developed because they needed to account for trade and logistics for their military. Other ancient societies used a base 10. The Egyptians, they used a base 10 system. But base 10 is not the only way to count. Counting in groups of 10 is not the only way to count. You could count in groups of 2, or you could count in groups of 12, or you could count in groups of 60, like the Babylonians did. So if you count in groups of 12, that's a base 12 system. So the way that might work, the Hawaiians had a base 12 system. You would count 1, 2, 3, 4, 5, 6, 7, 8, 9, and then at this point, you would have to come up with a new symbol to represent your number. So here's a symbol we could use. Let's just use the symbols from the Schoolhouse Rock, where we call that deck, L, and then either 10 or do. So the number of things we're counting here, this is a total of 12 things that we've counted, but we don't spin the dial over on our odometer. Oops. We don't spin our dial on our odometer like this odometer here over until we've counted 12 things. And then the next dial also has 12. And the dial after that has 12, so on and so forth. And so if we were to continue on then, after the 10 term, we'd go 11, 12, 13, 14, 15, 16, 17, 18, 19, dec-teen, L-teen, 20. But this would represent, and I'm going to write it instead of using a number, this would represent the 24th thing. So you're thinking maybe this sounds screwy, but that's only because you're used to a base 10 system. And the number system that we use is really kind of arbitrary. So you can imagine a Babylonian system with a similar idea as this, where they had 60 different characters. And their dial, instead of 10 or 12, has 60 characters on it. So those odometers would be huge if we had cars that had base 60 system. So the idea that this is kind of arbitrary, and the fact that base 10 has is pretty much universally accepted right now in across the world. But a lot of societies use these other base systems initially. And a base 12 system has a lot of advantages to it. First of all, there's a lot of factors in 12. There's 3 times 4. There's 3 times 2 times 2. There's 2 times 6, 2 times 3 times 2. There's all sorts of, there's so many more factors, and this can make life easier for you. It's also easier to deal with ideas like a third of something when you have a base 12 system, because then you aren't going to end up with a whole number, as opposed to this a decimal that goes on forever. And actually, some people talk about the advantages of the base 12 system would make computing. There'd be some advantages in computing too, and coding of different types. So actually, a base 12 system actually probably would work better for us, but that's not the system we use. So base 2 system we might call binary, and the binary odometer might look something like this. And in this case, each of the dials only has two numbers on it, a 1 or a 0. So if we were going to count in binary, we might do something like this. So I have set this up here. So it would start again as 0, and we'd have 0 things. And then when we have, actually with 0 things, I'm just going to leave this up as a blank. And then we would have 1 thing, or 1 in base 10. So this would go to 1. This would still be 0, 0, 0, 0, 0. And then when we had 2 things, maybe 2 peanuts, and base 10, that would be 2. But it's not, there is no 2 here on these dials. These dials only have a 1 or 0. So this would hit 0 again, and this would hit 1. And of course, all these are still going to be 0 out here. So a 1 followed by a 0 is equal to a count of 2 in binary. And so if we had 3 things, and base 10, we count that 3, then 3 things, this would now spin again, and we'd have 1 here, and this would still stay 1, 0, 0, 0, 0. So 1, 1, that's a 3, and then let's just do one more. So with 4 things, this would flip again, and if this flipped, that would cause this to flip, so this would go to 0, and then this would go to 1. So something that looks like 100 to us with a base 10 system, actually in a base 2 system, 100 represents a count of 4.